In our study of mechanical vibrations, we'll start with a frictionless mass connected to a spring, which is pulled back to X max and released. And we know that our free body diagram will look like this. It'll have an F is equal to negative Kx on it when it's released. And using Newton's law, sum of the forces in the X is equal to MAX. We have negative Kx is equal to M. X double dot is what we'll write for AX. And dividing by M, we get our characteristic equation where we know that the general solution for this form of equation is a sine and cosine type function, which we write as x is equal to a cosine of omega t plus b sine of omega t. And a and b are constants which depend on where we release the system from rest. For example, here at t equal to 0, x is equal to x max. So a would need to equal x max. If instead we had started at t equal to 0, x equal to 0, we'd find that a would equal to 0 and that b would be some value. So the a and the b are really dependent on where we start in our oscillatory motion back here. And knowing that, they can be combined into some generalized solution. X is equal to x max sine of omega t plus phi, where the phase angle lets our sine and cosine functions merge and be written as one function and allows it to start at some place other than at the origin. Here's our classic sine function, and at t equal to 0, x is 0, and at pi on 2 it reaches a max. But let's say that we were going to start the clock at here, at this is t equal to 0, but we still wanted to use our sine function. Well, we phase shifted it by pi on 2, so we could define this as omega t plus pi on 2. And then check for t equal to 0, we'd have sine of pi on 2, which would start us here. So by using a phase angle in that, we can just use the sine solution instead of having to keep a mix of both sine and cosine. And that's useful particularly if it was someplace here. If we started in the middle between the two nodes, we'd end up keeping sine and cosine in this form, and yet here we could write it with a phi is equal to pi on 4, let's say. Something else that's important is that we recognize that omega is the square root of k on m. We call that the natural angular frequency, and it has units of radians per second, or really just cycles per second, which is seconds to the minus 1, or hertz. And we know from our studies with spring systems that omega is equal to 2 pi f, which is 2 pi on the period. So from that we can get the period of oscillation as 2 pi on omega, or 2 pi square root of m on k. In summary, when we're working on a vibrating system, we try to recognize the characteristic equation, and whatever constant is in front of the x we know is going to be our omega squared, so we can use our natural angular frequency equation to solve for that. And we know the general solution will be a sinusoidal type, and that we could always solve for the natural period of oscillation using the period equation. And in general, we're not going to derive these equations using differential equations every time. We look for the characteristic equation and we'll jump right to the solution set. And this is a key factor in understanding mechanical vibrations. We want to look for these patterns and apply them to the system. Here we have a large disc suspended from a steel rod, And the steel rod has what we call a torsional spring constant. It would have units of Newton meters per radian. As we rotate the disc by an angle of theta, there'll be a moment here of minus k theta, trying to restore it back to the theta equal to 0 position. So it works a lot like Hooke's law, F is equal to kx, except in this case it generates a torque or a moment. If we release it, we find that it'll oscillate back and forth in this fashion. We can apply a moment equation to the center of this thing, so the sum of the moments about g will be I g alpha, and the moment will be minus k theta, and that will equal I of the disk times alpha. We could write alpha as theta double dot. And if we divide through by I of the disk, we'll get theta double dot plus k on I of the disk. Theta is equal to 0. We recognize that to be our characteristic equation, and that term, whatever in front of this theta, has to be the omega squared. So the omega will be the square root of k on I of a disk, which will be the square root of k on 1/2 mr squared. So we know the natural frequency now of this to be 2k on mr squared. And the period of oscillation then will be 2 pi times the inverse of that. And the point is that we don't derive this from basic principles. We recognize the characteristic equation, and from there we can infer the solution right away without having to redo all the steps. Now, a side comment that I'd like to make on this is that we're generally using forms of Hooke's law. So we had it here. That torque is a rotational force. Theta is a displacement, which is like x. So this becomes our effective k in Hooke's law. And that's one of the reasons that that worked. Now, for my friends who've taken solid mechanics, that we have an equation for torsion in a rod where the torque will be phi j g on L. And let's manipulate this so that it looks like Hooke's law. So the torque is the rotational force, and that's our displacement, which is like x. So if I rewrite this as torque is equal to j g on L phi, this has basically become F is equal to k x, the effective k of that rod. And in fact, that would be the capital K for this bar. It would be j g on L. We could compute it from material properties and geometric properties of the bar, for those of you that have seen that. Let's take a look at the interesting case of a simple pendulum, where our free body diagram, we have mg acting here. Breaking it up into components, we would have an mg cosine of theta acting here, and an mg sine of theta acting here. This length is L. It's a lightweight string. And let's do this in the r hat theta hat direction. And we would also have then a tension force here. And in the theta hat direction, some of the forces in the theta hat would be m a theta hat. We have simply negative mg sine of theta is equal to m to r dot theta dot plus r theta double dot. In this case, where r is equal to L, and it's a constant, so r dot is 0. We can divide through by m, and if we divide through by r, which is equal to L, we get, when we rearrange this, theta double dot plus G over L sine of theta is equal to 0. Now this is close to our characteristic equation, with the exception that we have x here, which is a linear function, and over here we have the sine of theta. So technically, this does not fit this case. However, there's a small modification we can make here, and that is for small angles, typically less than 15 degrees, the sine of theta is approximately equal to theta in radians. So if we make a small angle approximation here, this does reduce to, in which case this does match our characteristic equation, and right here that value is omega squared, and immediately we can say then that omega is the square root of G on L, the period be 2 pi square root of L on G, which is the accepted period for a pendulum, and the motion could be defined as theta is equal to theta max sine of omega t plus phi. So the method for analyzing vibrational systems is to look for our characteristic equation, and when we match up the characteristic equation, we can pull out whatever is equal to omega and substitute it into our general solution set. Now you might ask, could I solve it in this form? And the answer is not easily. At best, we could rearrange this as theta double dot is minus G over L sine of theta, and recall that theta double dot is theta dot d theta dot d theta. If we bring the d theta up to here, we could integrate this, and we'll get that theta dot squared on 2 is positive G on L cosine of theta plus C1, and at theta equal to theta max, theta dot was 0, so C1 will be negative G on L cosine of theta 0, at which case we have theta dot squared is 2G on L cosine of theta minus cosine of theta 0. And we can take the square root of that. And that gives us a value for omega at any given point. However, the next step, which would be to say that that omega is d theta dt, where there's the time for this oscillation to occur, dt, rearranging it, would be d theta over the square root of 2G on L cos of theta minus cos of theta 0. And that is a fairly complex integral. It doesn't have an open solution to it. So at this point, normally we would go to a numeric solution. There's no easy solution by hand for that. However, for small angles, our approximation works, and as long as we don't go too far past 15 degrees or so, we get a reasonable approximation for a simple harmonic system. How will this work if we have a uniform bar or some other shape hanging from our pivot point at O up here? Well, again, we'd follow the same basic steps. Our free body diagram says the center of mass would be here, and that would be mg, and this would be L on 2 to that point. We'd have the same set of components here. So we'd have an mg sine of theta. And now what we would do is take the sum of the moments about O, where the sum of the moments about O would be I O alpha plus mrg cross A of O. And O is a pinned point, so the acceleration of point O is 0, and we get just this. And we have then that negative mg sine of theta as the force times the distance, which would be L on 2, will equal I about the end, which would be 1/3 ml squared alpha. And we see that we can divide through by m. One of the L's go, and then that's about it. We also know that alpha is theta double dot. So rearranging this, we'll have theta double dot plus 3g sine of theta over 2L equals 0. It's going to be approximately theta for small angles, at which point we have theta double dot plus 3g on 2L. Theta is equal to 0. Pause it and you write down what the period of oscillation for this rod will be. And looking at it, we know, since it's in the characteristic form, that that is omega squared, and therefore omega will be, and t then will be 2 pi square root of 2L on 3g, which is the period of oscillation for that rod. In fact, we can look for a general solution for the oscillatory period of an irregular object by applying the same steps. So again, we would have an mg here. The mg always acts at the center of mass, and like before, we'll have our mg sine of theta. And taking sum of the moments about O is equal to I O alpha, where we know that O is a fixed point, and we'll take this as the positive alpha direction. We get negative mg sine of theta times rg equals I about O of alpha. And our form will be then theta double dot plus mg rg on I0. We know that we'll do this for small angles, so I'll write sine as theta equal to 0. Again, just forcing this into the characteristic equation, and then right here is our omega squared. So omega will be the square root of mg rg, the distance to the centroid, divided by I, about the pivot point of the system. And that'll give us the omega for any irregular object, and the period then would be 2 pi times the square root of I0 over mgr. So there's a general form that we could use for any shape that's suspended. Here's one for you to try. We have two bars connected into a T shape, and they're both of length L and mass m. They're pulled back by a small angle theta and released. Find the equation that represents the period of oscillation for that system. If you found the center of mass to be 3/4 of L, you're doing great. The mass moment of inertia about 0.0 will be 17/12 ml squared. We have to use the parallel axes theorem on the lower bar. Omega, our natural angular frequency, turns out to be the square root of 18g over 17L. And if you didn't get that, could it be because the mass of the system is 2m? So be careful when you plug that into the center of mass equation. Then lastly, for step 4, we get simply t is 2 pi square root of 17L over 18g, which is surprisingly close to 1. So this is almost 2 pi square root of L over g, which is the period of a regular pendulum. So having that bar at the end, this thing starts to behave much more like a concentrated mass at the end rather than a T-shaped distributed weight. So interesting application, and thanks for trying that. And kudos if you got that on the first shot. Let's look at the case where we take a lightweight beam, such as a meter stick, and we drop a heavy mass on it. And the beam will start to oscillate up and down with the mass on it at the center. A key equation is that we need to look for some kind of F is equal to minus Kx. We call that a linear restoration force, which is a requirement for true simple harmonic motion and our characteristic equation to work. Now in this case, we have a beam that's being deflected by a weight at the center, and we have an equation for that. People who've taken solid mechanics will recognize these beam loading deflection tables, and what these tables show us is the amount of deflection for a given load under different orientations. Here that's a centrally acting load, here it's a uniformly weighted beam, here is a cantilever with a load at the end like a diving board, and here's the weight. And we can use this deflection equation here to represent this scenario, where we have the deflection y is negative p L cubed on 48 EI, and E is the Young's modulus of elasticity, I is the area moment of inertia, and if we have a rectangular beam, the I would be 1/12 BH cubed, and P will be the load, which in our case will be mg, the mass that's placed on it, and we'll assume that the beam itself is lightweight. Otherwise, we'll include this term as well in our calculation. And the trick here is to manipulate the deflection equation so it looks like Hooke's law. So the force is P, so let's rearrange this as P is equal to 48 EI over L cubed times Y. And if we do that, this is starting to resemble F is equal to Kx, where X is your deflection, in our case it's Y, F is the load that's applied, and K is the equivalent spring constant, we call it K star, or K effective. Now if we look at the deformation of this, there's a restoring force trying to push this back up as we deflect it, and that force would be described by this equation right here. So we can write then that sum of the forces in the y is equal to MAY, and we'll have negative 48 EI over L cubed y, and that's got a negative on it, is equal to M, and AY we'll write as y double dot, and dividing through by M, we get y double dot plus 48 EI over L cubed M, y is equal to 0, and once again, characteristic equation, there's our omega squared. Now it turns out we could have done this in an even easier way. Once we recognize the linear restoring force, and this equation down here is linear, as we apply a load P, we're directly deflecting y, and those are our constants. We could have just said that omega is the square root of K effective on M, the oscillatory mass, and we would have gotten the square root of 48 EI over L cubed M, and we would get the same value without even going through the steps of setting up the characteristic equation. So once we become comfortable with the equations and how they work, we can even just look for the restoring force. And from the restoring force, we can jump right to a solution for the period. If you'd like to try this calculation yourself, assume that we set up a meter stick that's 1 meter long. Here's its cross section, 4 centimeters by 1 centimeter roughly. And we'll drop a 10 kilogram mass directly on the center. Find the time for it to rebound and bounce back up. And here is the E of wood, it's approximately 10 GPa, and there's the I. Find the period of oscillation. And you should get a full period of oscillation of about a half of a second. And if we're going to time how long it takes to go down and bounce back up and then leave contact, you could argue that that's a half of a cycle, so that would be about a quarter of a second. And these are all approximate because really we should be including the weight of the stick as well, although the stick is only about 200 grams, but we could include the weight of the stick here as well, and you could even come up with the value for an oscillating stick. Okay, one last one just for fun. We have a heavy bar of length L and mass M, and it's supported at the right end by a spring with a spring constant of K, and we'd like to determine the period of oscillation for this bar if we pull it down by a small angle theta and release it. So setting up our free body diagram, we have a center of mass here, mg, and if this is going to be the equilibrium position before we displace this bar, that means the spring has already been stretched by some distance, which we'll call y0. So we have a spring force up as a result of that. Otherwise it wouldn't be an equilibrium, it would droop from here. And at the equilibrium point, we could say that the sum of the moments about O has to be 0. It's not moving, it's just sitting here. And we get from that mg times L on 2 will equal ky0 times L. From here we see that the L's drop out, and we end up with a requirement for equilibrium of mg will be equal to 2ky0. That's an equilibrium requirement. Now let's displace the bar downward by a small angle. So we have a delta y that we push it down with and release it. Taking the moments about point O, we get sum of the moments about O, be IO alpha plus MRG cross A of O, but O can't move, we know that. And we'll pick this as our positive direction. And we get mg L on 2 cosine of theta for the weight minus k y0 plus delta y L cosine of theta is equal to 1/3 ml squared alpha. Now for small angles, the cosine of theta is approximately 1. So these all just turn into 1s. We don't have to worry about them right now. mg, we found over here, is 2ky0. So let's put that in. So we get 2ky0 relating everything to the spring. Minus ky0L minus k delta y L is 1/3 ml squared alpha. And back here these 2's go. And we end up with a ky0L minus a ky0L, and that drops out. And that's not uncommon when we're working with equilibrium conditions. We see things like that a lot. Now this delta y here, since it's a small angle, delta y would basically be L theta, the arc length that we pushed this down. So substituting that in, we get minus k L squared theta is 1/3 ml squared alpha. Do you see where I'm going with this? The L's drop out. Bringing the constants to the other side, we can rewrite this as theta double dot plus 3k on m theta is equal to 0. And that's our characteristic equation. Therefore, that is our omega squared term, dot, dot, dot. So the patterns keep repeating here. Look for the characteristic equation and then recognize that the period will be 2 pi divided by omega, and we can get a good approximation for the natural period of oscillation. For spring-driven systems, we use Hooke's law, and we can often approximate other systems to be like Hooke's law, that is that they are linear, and we can look for our K effective, in which case omega will be the square root of K effective on M. And we can also substitute that into the period equation. And then we know that our general solution will be x as a function of time or of theta will be x max sine of omega t plus or minus some phase shift that it might have. Thanks for watching.